Okay, so we're starting the vectors unit, and first we want to kind of review a little bit from Math 20. So that was a while ago. Talked about mostly two-dimensional vectors back in Math 20, but a little bit about three-dimensional. So here are two vectors. Remember that your standard basis vectors are vectors I and J and K, 3 dimensions. So we could rewrite this as A times 1, 0. Sometimes I still do square brackets, but it's really round brackets in most of your notes. And then B times 0, 1. Okay, those are the standard basis vectors in component form, 1, 0, 0, 1. So I corresponds with x-axis, J corresponds with the y-axis, and K with the z-axis. So this would be A times 1, 0, 0. Okay. So a position vector of any point, for example, point A with components A1, B, and A2, then the vector from the origin to point A can be shown in the position vector in column matrix form. And so that's why I sometimes use square brackets as a column matrix, but you can have round brackets as well. Okay. If we were to graph that, so for some reason we don't have the graph on here, but you guys have it. Okay, so vector, let's say there's point A. Okay, so it would have coordinates A1, A2. Okay, starting with the origin. All right, so its x component is A1 and its y component is A2. This would be A1, this would be A2. Okay, so when a vector, so how does a vector and its negative correspond to each other? Well, they're called opposite vectors. So they'll have the same magnitude but opposite direction. So, for example, the opposite of this vector up here would then put the arrowhead at 0, 0, and it starts at A. So the opposite you could, so basically for that last one, if we have OA and we want to take the opposite of that, that's the same as AO. Okay, so you're just changing the direction. If you add vectors together, doesn't matter what order you add them, so that's the commutative property. Just like numbers, it doesn't matter. If you add two vectors together and find the resultant, and then add a third, it's the same as adding the first one with the resultant of the next two. That's the associative property. So really, adding vectors doesn't matter. Adding, subtracting, what order. If you're multiplying the sum of vectors by a scalar, okay, that means just a number, then you just distribute that number. Okay, so it's basically like stretching each vector by the same amount. Okay, then remember you're adding vectors. So tip to tail means you start with, say this is vector u, and if we have vector u there and vector v here, then this is u plus v. We're starting at its tail, okay, then going to the tip, and then the tail to the tip. So the arrowhead and the beginning have to match up. And then the diagonal form from the tail to the tip, and there's your arrowhead, that's the sum, okay? Parallelogram is basically if you have the tails together. So there's vector u, and then this is vector v. So if that's how you've drawn them, then how do you get the resultant of that? Form a parallelogram, and then it's the diagonal. Okay, so if you take a look, I use the same vectors u and v, and the the sum is the exact same vector. It's just underneath here, right? It's parallel. Okay, so hopefully that kind of rings a bell. Subtracting vectors. So let's say this is u and this is v. So again, tails together. If we join the arrowheads of those two, okay, so then really think about what's happening here. So this arrowhead is at the end, so it's going to be vector u, and then you're really going backwards from there, so you're subtracting vector v. Kind of like saying if you have vector u here, and if you add negative v, then that is, there's negative v. So now your resultant from the tail to the tip there, that's the same vector as this one that was drawn. Okay, location doesn't matter. So that's u minus v. U plus negative v is the same as u minus v. So basically, for subtracting vectors, look at where the arrowhead is. It's going to be that vector that gets you to the arrowhead minus the other vector, as long as they're starting tails together. Okay, midpoint of a vector AB. Okay, so there's vector AB. A little bit hard to see the arrowhead, but it's there. We can tell what the midpoint is in this one because it's on grid paper. Okay, and basically, so this is in the coordinate grid. So U might be, O might be over here, the origin, right? So here's your vector OA. There's your vector OB. Okay, and then this would be your midpoint. So that's your vector ON. So, how do you get ON? Well, think about traveling along the vectors here. OA gets you up to the line, and then you're going along AM. All right? That gives you the vector ON. That's what you want to find. Well, what's AM? If that's the midpoint, that is half of vector AB. Okay, so we can replace by half AB. Okay, so then what's vector AB? Like, we don't know what that is, but we know the endpoints. Well, AB is vector OB minus vector OA from what we just talked about subtracting. Okay, so that vector AB you can replace with this. Then if you basically expand out, multiply through by half, collect like terms, you get a half OA plus a half OB. So half OA plus a half OB. Okay, so basically is parallel to that. So there's a half OA. Here's a half OB that we want to go tip to tail. So that's going to be up 1 to the right 4. So up 1 to the right 4 gets you to OM. Okay. I guess you could show that as a half of OA plus OB. Okay. All right. So now doing some more work with basic vectors. Okay, so vector represents a displacement or a translation. A vector can be shown as a directed ray with a distinct length, meaning that it has a beginning and an end with an arrow to show the direction. Vector can also be represented by a ray without a specific length or represent direction. Vectors in 3D space can be shown using representation of a three-dimensional plane consisting of 3 axes. The co-perpendicular is shown below, x, y, and z. So take a look at the orientation here. So normally when we do a two-dimensional, we have x and y. Now the x is coming out of the board. So really, we see this two-dimensional if we look down from above. Okay, and basically turn your head to the right and look down from above. There's your y, there's your x, and then your positive z is coming out at you. So here, the positive z is coming out at you, but the normal representation is that x and y, that plane formed is parallel to the floor, right? And then the z's coming basically like the wall. So if we were here in person, I'd go to the corner of the wall and say, okay, our x is the window ledge, our y is the chalkboard ledge or the whiteboard ledge, and z is the pillar that's at the corner where the clock is on. Okay. So, given those vectors, determine the following. So basically, we want to simplify these. We're just going to keep them in their standard basis vectors, I, j, and k. So really about algebraic skills. So if we're going to add these, we're really 2i minus 3j plus k plus I plus 2j minus 4k. And you're adding, so it's just like terms. 3i minus j minus 3k. Then subtracting. Okay, so collecting like terms. And then multiplying through by scalar first. You know, I have room here. So 8i minus 12j plus 4k plus 3i plus 4j. Plus 8k, and then collecting return 6i minus 16j plus 12k. All right, and then the magnitude of v. So remember back to Math 20, that's where you take the square root of the squares of the components added together. So that's going to be 4 plus 9 plus 1 is square root of 14, and reduce it if you can. W, 1 squared plus 2 squared plus root of 4 squared. Because remember, when you're multiplying these values, this here, that really simplifies to 1, I'll do it round brackets, 1 to negative 4, right? Here, this is equal to 2, negative 3, 1, because of those standard basis vectors. So it's 5 and 16, that's root 21. And the unit vector in the direction of W. So, let's think about it. Got it, this is, say W was a two-dimensional vector, like this, okay? So that has a particular magnitude. We want it to just be a magnitude of 1. So say this vector here had a magnitude of 10, okay? The direction that it's going, that arrow tells you what direction. If we want the unit vector in that direction, we want the same line, same vector, with a magnitude of 1. So we're really dividing the original by 10. We're dividing by the magnitude. So if we want the unit vector of W, then we want to go 1 over the magnitude of W times W, vector W. So the magnitude of W we just did, it's 1 over, it's root 21, so that's going to be 1 over root 21 times vector W. Okay, and you're done. Sometimes we might want to rationalize that. Oops. Sometimes we don't actually rationalize. Okay. Now, unit vector of W. So in this case, then you could actually show it's going to be that times the component form 1, 2, negative 4. Okay. Oftentimes we leave that out unless it does simplify. Okay, so that's the unit vector for W. Or you could leave it in these with the standard basis vectors. So it equals root 21 over 21. And then that's I plus 2j minus 4k. Okay. And that's it. So then, the dot product. So remember the scalar product, also known as the dot product or inner product. What do we do to get to that? We multiply each component together and add them up. Okay, so V1 W1 plus V2 W2 plus V3 W3. So here, the dot product, I call it the dot product. IB tends to call it scalar product more often. So how do we show that? And then negative 2 plus 0 plus 3 is 1. You don't even have to show that work for it. Okay. Okay, so now we're actually going to prove the dot product between the component form and the geometric form. So if we draw a diagram here of two vectors, u and v, okay, that are joined at their tails. I'm just going to do this. So if I call, or not u and v, I'm going to call v and w. All right. In here, just a hint using the cosine law. So if I have those two vectors joined at their tails, and I'm using the cosine law, we know the angle in between them is theta, and I can join this, the tips up with a vector. Okay, that vector will be v minus w. Okay, and so now we've got a right triangle, not a right triangle, a triangle that we can use the cosine law for. We are relating it to angle theta, then the side opposite theta is vector v minus vector w, the magnitude of that. So in the cosine law, this would be the magnitude of v minus w squared, and then each of the other sides minus 2w cosine theta. I have you, yeah, it doesn't matter whether, maybe I'll keep these in order v and w here. It doesn't matter though. There we go. And so you can see, this is what we're trying to prove, trying to solve for. And so if we put the rest in component form, then hopefully we'll get the left side. So do that. So you can see here, V1, V2, V3. So our definition for V is V1, V2, V3. For W, W1, W2, W3. Okay, so this will be V1 minus W1, V2 minus W2, V3 minus W3, magnitude squared, then V1, V2, V3, magnitude squared, W1, W2, W3, magnitude squared, and then I'll leave the rest in their geometric form, because that's what we want to solve for. Okay, so nice thing, when we're squaring, so magnitude will be square root of the sum of the squares of each component. Squaring that we'll get rid of the square root. So really, we'll end up with v1 minus w1 squared plus v2 minus w2 squared plus v3 minus w3 squared equals v1 squared plus v2 squared plus v3 squared. v3 squared. Sorry. I had it right before. v3 squared, then plus w1 squared plus w2 squared plus w3 squared minus 2 magnitude of each cosine theta. Expand those out. I'm just going to put that underneath because I'm getting one out of space. So minus 2 Okay, now like terms. So v1 squared, v1 squared is with that, v2 squared is with that, v3 squared is with that, w1 squared is with that, w2 squared is with that, w3 squared is with that. So, get negative 2 v1 w1 minus 2 v2 w2 minus 2 v3 w3 equals negative 2 v, w cosine theta, divide by negative 2, and we get what we're looking for, v1 w1 plus v2 w2 plus v3 w3 is magnitude of each cosine theta. Okay, so this is the geometric form, this is the component form. And we can use that to find things like angles between lines. Okay, now looking at the visual representation, so in this case, two vectors are shown, v and w, different ones from last time. Now w is the horizontal. Really what the dot product is, it's kind of like force in science. It's the, so magnitude of the direction, so if you draw a perpendicular from V onto W, this vector that's formed here is called the projection of V onto W. That vector there, the notation is vector V with a little w, so that means it's a projection vector. And it's like having, if you had a light shining down from above, the projection vector is the vector, it's the shadow underneath V. Okay, that's how I think about it. So that's the projection vector. What the dot product is the magnitude of that projection vector in the direction of W. Okay, now if we call this angle theta between the two vectors, then remember we've got a 90-degree triangle there. So cos theta is the adjacent side, which is the projection vector, magnitude obviously, over the hypotenuse. Now, if we solve for the projection vector, we can now replace that into the definition of the dot product. So therefore, dot product equals magnitude of V cos theta, magnitude of W, and then just rearrange them. Okay. So, as I said, we're going to use these to calculate different things. And so here are some of the properties of the dot product. Okay, so dot product equals 0, then they're perpendicular. Dot product's order of taking the dot product doesn't matter. Okay, multiplying the dot product by a scalar, you can, the order doesn't matter for that. You either do the first vector by the scalar or the second one. If you're adding two vectors and then taking the dot product with something, it's kind of like the distributive property, but with dot product. So you basically take the dot product with each. And this one is a repeat. So that is out. And then when you take the dot product of vector with itself, you get the magnitude squared. Okay, so that's kind of an important one too. It's helpful at sometimes, right? Really, that means the angle between the two vectors is 0. And so when you take cos of 0, it's 1. So you get each vector magnitude multiplied by itself. Okay, so are these determine A if these are perpendicular. So that means the dot product has to equal 0. So here, 2, 3, negative 4, dot product 3, 6A has to equal 0. So then that's what, 6 plus 18 minus 4A equals 0. So 24 equals 4A, A equals 6. Okay. Then determine the angle between these. So that would mean you're taking the dot product in component form, and it's going to equal the magnitude of each. Cosine theta. If you want to solve for cosine theta right away, you can. I can do that now. So my dot product here is 15 plus 0 minus 4, which is 11. Divide by, magnitude here is 9 plus 4 is 13, plus 16 is 29. And then 25 plus 1 is 26. Okay, so then you can go second. Oh, you need to be in degree mode. Second cos. 11 divided by square root, and you can just do 29 times 26 underneath the square root. And so theta equals 66.4 degrees. Doesn't say what to round to. We'll go to the nearest 10. Sometimes we might say the acute angle in between two vectors. And so you would subtract. That would actually be more with equations of lines, so you don't have to worry about that. Okay, next one.